grandfather's work was doo-doo. I am not interested in death. The only thing that concerns me is the preservation of life.
All right, radio fans, KBYP back in the saddle doing very detailed and comprehensive signal and noise testing. I've tried every reasonable combination of good, perfectly matched 40-meter dipole, perfectly matched at 7.0003, if I got the right number of zeros in there, 30 kc up from the bottom of the 40-meter band, with combinations of the proper antenna with the, oddly enough, the shield disconnected at the receiver. The noise goes insane. And then a similar length of transmission line connected to the receiver. It's the line off the 80-meter antenna. I just unscrewed it and dropped it on the ground. Unterminated on the far end and terminated on the far end with a dummy load. And then, since there are no reliable signals across the 40-meter band, up and down, to compare with noise readings, I then reconnected the dipole to the Kenwood, connected the transmission line to the ASU set at 1 watt CW. It's broadbanded, so I could transmit 1 watt, measured on the bird into the dummy load, and there's enough leakage out there that it couples 60 feet up into the 40-meter antenna and or the transmission line, which is laying on the ground in parallel, not probably 10 feet apart. The Kenwood is a much better analog receiver, no DSP to make the noise go away, with a real S meter instead of the Mickey Mouse unreadable bar graph on the ASU. Long story short, the only way to go, not only on transmit but on receive, is a properly terminated, resistively matched antenna. And no, you don't have to have that to find that, but it sure is nice. But the point is, the data shows that when the receiver is tuned either side of the resistively matched frequency of the antenna, both the signals and the noise go down. Well, that's what we'd expect. The antenna is mismatched. Tuning the receiver from 1 up to 9 megahertz shows what's known about atmospherics. The noise peak, the natural noise peak, is at around 8 megahertz. And that was consistent in all the tests except for the test where the transmission line is unscrewed at the receiver. Then that goes away. Something else happens. But the mismatched antenna is not the cause of higher noise. Not natural lightning storm noise in Europe, whatever. Contrary to popular belief. And contrary to what I believed. Here's the quickly taken chicken scratch data. Left side broadband noise peaking at about high 7 megahertz. About S2.3, give or take a little bit, 7.6 megahertz, 3.5. It goes down to pretty near nothing at 6 megahertz. With the shield disconnected at the receiver, the noise goes through the roof. S9 at 8.23 megahertz. And 8.23 megahertz and 5.2 megahertz. The received noise on the antenna system at 5.2 megahertz is half S unit. But the 8.23 and 5.2 megahertz figures are where the asymptotes for the 40-meter antenna are. In other words, there's some kind of match in between those frequencies, but at those frequencies, the antenna is basically a short. At those frequencies, the antenna is basically a short across the end of the line. That's basically the same as a shorter transmission line. We expect pretty much a total reflection. Disconnect the shield, and you know what breaks loose. S9 at 8.23 instead of 1.7. Minimum is about S6, around where the antenna is matched, going up to S9 down at 5.8 megahertz. Extreme noise and an extreme increase. And that right there cuts out pretty much any signal on the bands these days, except those illegally running power amplifiers in the US. Next page, received noise on just a transmission line lying on the ground, dummy load on the other end, 2 kW homebrew dummy load in a paint can. S nothing. A couple of birdies here and there, either from probably broadcast band carriers, because the other antennas are coming in here and they're coupling noise through the air. So there's a birdie here and there. With the shield disconnected, the noise from 8.23, about 8.5-ish units steady, 6.8 megahertz, 3, 6.8 megahertz, S3, 5.8, 8.5, 3 megahertz, 8.5, 4.8 megahertz, 10 over. But down below 3 megahertz, S7 to S9, kind of a generalized noise. But what I observed is that when the frequency gets down around a couple of megahertz, the background noise, so to speak, the band noise from the natural sources goes away and the background gets quiet. And going from about 7 megahertz on down there, periodic peaks in the noise, spaced irregular spans apart in frequency. And what is living down at the bottom of the in the low frequency bands is an extremely strong signal at 855 kilohertz. S9 plus 30 with the shield disconnected, just screaming hot. And it's also appears at about 1778 and 1790 kilohertz, which proves they're not harmonics. It's some kind of active noise source, probably from the AC line. I'll have to do a whole house power shut off and check it on battery, see if it's in my house. But I think it's power lines. Well, that doesn't allow testing signal relative to noise, and there's no signals on the 40 meter band or any of these bands that are that broadbanded and relative. So I transmitted on the ESU857 at 1 watt through that 80 meter coax that's terminated in the dummy load, and let the leakage couple up about 40 feet up to the 80 meter or the 40 meter antenna. And what I got was a relatively steady 20 over received signal on a 40 meter dipole from 8.3 megahertz. Actually, the signal levels went down considerably from 6.6 up to about 7.4 megahertz. Very important. And below that, going down towards 5.2 megahertz, back up to 20 or 30 over. What that implies is that when the antenna is matched, the transmission line becomes self-shielding. The noise with the transmission line into a mismatched antenna, the transmission line's picking up noise and a train load of it, because the transmission line on the 40 meter dipoles is longer than almost twice as length of the antenna, and most of it's laying on the ground. With the shield on the transmission line disconnected at the receiver, the noise skyrockets to 50 over. That proves basically 40 dB worth of coupling between the two transmission lines, because one now is grossly unterminated, and the receiver is looking into just the center conductor of the transmission line. So here's why that we can't have a mismatched tuner kludge at this end, because it tears the receive up, and we can't have a mismatched antenna on the other end, because that causes both loss of signal and atmospheric noise, but it picks up local noise sources. And this is exactly why the majority of hams aren't on the air, and very, very few of them are doing DX. Most of the DX I've worked has been at S5 or less, some of it closer to S0. Essentially no copy over the noise. A couple years ago, DL1 BUG in Germany was complaining about local noise Germany, high population density, lots of electricity and electronics, a lot of noise. Where I'm out here in the country, I'm lucky. But he was saying that he couldn't copy anything much under, I think it was an S6. So for all these mismatches, especially the fake tuner at the receiver, hose up that match, and all you know what breaks loose. Give you up to another 40 dB worth of noise. It's not going to be that much. There's going to be an increase, especially if there are other noises coupled by the ground through the power utility, the neighbor's wall warts, the charger in the garage, whatever. Some sources, arcing power line connectors, things you can't get rid of. The only way to get rid of them is to fix them. The only way to hide them is to have the antenna properly matched. And that additional S5 to S9 noise is why the majority of us are not on the air. It's not bad propagation. Yes, propagation stinks. But the signals we're trying to receive from Europe are not like they used to be with good propagation of S9 and 15 over. A lot of them are S4 or 5. And if there's a S6 to 9 north flow at your shack, you're done. You have no hope of receiving it. If you can't receive them, you can't work them. So there's the story of how transmission lines pick up noise, KBYP, dit, dit. And a correction at the end. At 8 minutes and 37 seconds into this video, I made a significant mistake. The increase up to 50 dB from disconnecting the shield at the receiver is a transmit signal from the Yaesu 857 into the dummy load. But that energy is being coupled into the antenna transmission line and not the antenna, because there's no variation, or not much variation, a couple 5 dB across that spectrum. And when it's the antenna working and the antenna match changes, there's a significant difference of 5, 10, 15, 20 dB. Now you might notice I said that this antenna is optimum at 30 kc above 7 megahertz, which is at the 7.0 plus 15 dB. Notice the received signal strength is minimum at 6.6 megahertz. Why are they different? Well, I can't answer that at the moment, except to notice that the transmission line for that antenna is 135 feet long. Figure how long the wavelength is for 40 meters. Might be a relation there. So, excuse the mistake. The huge, tremendous increase here is 55 dB worth of transmitted signal from the 857. That's not noise picked up, like I said, at 8 minutes and 37 seconds.